Welcome, this is Dr. Plague, and in my last video I designed and coded up a simple assembler for the Plague Mark II homemade CPU, and I wrote a simple script to program the output of that assembler into a flash memory chip. And while it's not necessary for you to have watched that video to understand this video, I am going to use the assembler and programming script to help write some code to test out the Plague Mark II CPU. Now, we already tested what we have so far, to a degree. But what I want to do is come up with something more practical, a kind of a real-life example. Something that might actually be useful. Now, of course, we would never build the Plague Mark II to perform the task that I'll be programming today, but I just want something a little more realistic. What I've chosen to do is to write a short program to turn the Plague Mark II into a watchdog timer. Now, trust me, this is not a watchdog timer that you'll really want to build, but rather it is just an example to play around with. For those not familiar with watchdog timers, they are simply timers used to monitor a processor or computer system and take corrective actions to help the system recover from a malfunction. In our case, I'll be monitoring a simple microcontroller, and the malfunction I'll be looking for will be some type of a lockup or unexpected infinite loop. The way this watchdog timer will work is that it will expect to be tickled by the microcontroller every so often. And if the microcontroller fails to tickle it in a timely fashion, then the watchdog will reset the microcontroller. To tickle the timer means to reset the timer. Some refer to this as kicking the watchdog. So, given the instruction set that we currently have for the Plague Mark II, how do you suppose we could code a watchdog? We don't have very many instructions to choose from, and we only have 16 bytes of program memory space. Let's first start with drawing up a flowchart of what we want it to do. This will be the start of the program. We need a timer, and that kind of implies that we need somewhere to store the current count of the timer. Currently, the Plague Mark II has one register, Register A. That sounds like a good place to store the count for the timer. Now, in order for this register to function as a timer, we need to increment it. In other words, we need it to count. I'm actually going to do something a little weird here, just to make this program a little more interesting. This is not how I would actually write a watchdog timer, but let's just go with it. What I'm going to do is kind of create two separate watchdogs. You'll see what I mean in a bit, and I'll explain it as I go along. I'm going to make the first watchdog count faster than the second one. So instead of incrementing it by 1, I'll increment it by 2. Therefore, the next step in the flowchart is to add 2 to Register A. Remember, Register A starts out with the value of 0 when the CPU first starts up, so it will start counting from 0 in increments of 2. I'm going to let it count up to 16 before attempting to reset the microcontroller. To do this, we'll check if the carry flag is set. If not, we'll jump back up to here and continue counting. If it is set, then we'll continue on to reset the microcontroller. After that, I'll clear the carry flag and reset the timer. Now, here's the interesting part. I'm going to code up another watchdog timer section after the first one. And, just for fun, I'm going to jump to the next timer section, as kind of a way to further test out this homemade CPU. The second watchdog timer will take more time to count up to 16. It'll take about twice as long. To do that, I'll just count in increments of 1 instead of 2. And while this is completely unnecessary to use two timer sections like this, I've decided to do it to help further test out the functionality of the CPU. The idea is that the microcontroller may take extra time when it first boots up before it starts to tickle the watchdog. Therefore, if this extra time is greater than the time it takes for the first watchdog to time out, then the second timer section will give it more time to start up. I know this sounds ridiculous, since we'll be unnecessarily resetting the microcontroller on its first boot, but this is just all for fun. So basically, I'll just do the same thing as before, but only increment the counter by 1 in each iteration. After we clear the carry flag and reset the timer, I want to restart the second timer section, so I can just check if the carry flag is set and jump back if not. And just to give it the finishing touch, I'll end the program execution if the carry flag is set, which could never be the case. So we should never get to this end if the program executes correctly. We'll be testing for this. Okay, so that concludes the flowchart. Now we need to translate this into assembly language instructions for the Plague Mark II CPU. We'll start at memory address 0. We don't need any instructions for the start, but I'll just write the current address before the assembly language instructions. To add 2 to register A, we can use the add instruction, add 2. The next instruction will be at address 1, and we have an assembly instruction to check the carry flag. It's called jump if not carry, and we'll jump back to address 0 if the carry flag is not set. If it is set, we'll move on to address 2. Then, to reset the microcontroller, we'll just use the out instruction. This will output a high from our CPU, and we can invert that by using an inverter if needed. So, we use the out instruction to reset the microcontroller. But how does the microcontroller tickle the watchdog? This is actually very simple. The tickle signal will connect to our homemade CPU reset line. To reset the watchdog, we just reset the Plague Mark II homemade CPU. Now, at address 3, we need to clear the carry flag. How can we do this? We don't have any instructions for clearing the carry flag. For this, we need to get a little creative. We know that register A holds the value of 16 if we get to this point. Or does it? While we are counting from 0 to 16, register A can only hold values from 0 to 15. The carry flag is used as an extra high bit for register A, but register A only contains the value of 0 when we get to address 3. Therefore, to clear the carry flag and reset the timer, we can simply add 0 to the current register content of 0, and 0 plus 0 is 0 with no carry. The timer is now reset to 0 and the carry flag is cleared. Very good. Let's continue. I'm going to place the next timer section starting at address 8, and the jump is going to be at address 4, directly after the add instruction at address 3. We only have one jump instruction at this time, and that is jump if not carry. We'll use that to jump to address 8. Remember, we cleared the carry flag, so this jump if not carry instruction should always jump and never pass through to address 5. At address 8, we simply add 1. Then, at address 9, we perform another jump if not carry, jumping back to address 8. Then, just like at address 2, address 10 will be an out instruction for resetting the microcontroller. We can clear the carry flag and reset the timer the same way as before, with an add 0. Then, we want to jump back to address 8 if the carry flag is not set. Hence, jump if not carry 8. Of course, the end at address 13 will be a simple halt. And remember that the program should never get to this point and should never execute this halt if everything executes correctly. Well, that's it. Let's put this code into an assembly file. Notice that I'm adding some comments in here. I'll save this file as watchdog.asm. Then I'll assemble it. Good, no errors. And there's the final assembly. I'll use TerraTerm to program this with the script I wrote in the last video. First, I'll ID the flash chip, then erase it. Okay, let's start the script. Then I'll choose the assembled output file. And there it is. The flash chip is all programmed. Let's get it installed into the Plague Mark II. Now first, I want to wire up a couple more LEDs on our LED graph. We currently only have the first 3 address lines connected, so I'll connect the 4th address line so we can see the full 4-bit address. I'll just bypass the buffer IC and connect it directly to the LED. It should still work fine. Then I'll connect the out bit from the 238 3 to 8 line decoder IC, pin 13, to the last LED. This will allow us to see when the out instruction is executed. I still need to add a couple 470 ohm current limiting resistors from the LEDs to ground. Good, we should be all set to demo this. So, what should we expect to see? We should first see register A with carry count from 0 to 16 in increments of 2. Then we should see the out LED light up. That LED will turn off. Then register A with carry should clear to 0. Then we should see register A with carry count from 0 to 16 in increments of 1. And the out LED should light up again. And so on. Let's try it. So, I'll apply power. Then start the clock. Register A is counting by 2. It hit 16 and the out LED flashed. Register A reset to 0 and started counting again in increments of 1. Again, it hit 16 and the out LED flashed. Then, we repeat counting from 0 to 16 in increments of 1. Perfect! And we know that if I press the reset, the whole thing will start over. Good, this looks like it works. But wouldn't it be better to test this with an actual microcontroller to see if it can recover from a real lockup? Let's do it! What I have here is an ATmega 328 microcontroller which I've programmed with this here code. Basically, what it is going to do is wait for a while, about 10 seconds, to simulate a long boot up, during which time it will light up a yellow LED. After the boot up, it will turn on a green LED and tickle the watchdog on occasion, about every 4 seconds. I'll have a switch connected to it which will place the microcontroller into an infinite loop. During this infinite loop, a red LED will light up, and there will be no tickling of the watchdog. So, remember that yellow indicates boot up, green is normal execution, and red is a lockup. And I know that this microcontroller does have an internal watchdog that we could use, but let's just pretend it doesn't. And if we look at the code, I first set up all the unused input and output pins of the microcontroller. And notice that I bring the tickler high before setting it as an output. This will just activate the internal pull-up before it's an output. That way it isn't outputting a low before we bring it high. And I'll just connect an external pull-up to it. Let's see. Then I set up an interrupt to detect a switch press. Then the yellow LED is turned on, followed by a long delay of 10 seconds to simulate the boot up time. After that, the green LED is turned on. Then we enter a loop to simulate the normal execution of the system. During this loop, I tickle the watchdog and then create a 4-second delay. Pressing the switch will cause this pin change interrupt down here to execute. It turns on the red LED and then enters an infinite loop to simulate a lockup. So let's breadboard this little guy up. I'll connect up all the power and ground. And add a couple 10 mic and 0.1 mic caps on the rails for good measure. Then the LEDs with some 330 ohm current limiting resistors. I'm struggling with that one a little bit. It doesn't want to go in the hole. I'll just move it over here. Good enough. And I'll place a switch right here. I'll connect one side to the microcontroller and the other to ground. I don't need a pull-up for this switch since I've enabled the internal pull-up in the microcontroller. Then I'll add a 10K pull-up resistor to the tickler output. Okay, let's test this out quickly. When I power it up, the yellow LED lights up. And then, after some time, the green LED turns on. If I connect a scope probe, we can see that the tickler pin does go low on occasion. Now, I'll press the switch and the red LED lights up. There is no more tickling, and we are now in an infinite loop. There's absolutely nothing that I can do to get this microcontroller out of its infinite loop, short of cycling the power or resetting it. Okay, let's connect this to the watchdog timer. I'll connect up the power and ground to the Mark II. There'll be some resistance to this power connection, so we probably won't get the full 5 volts, but it should be close enough to work. Remember that the watchdog will output a high to reset the microcontroller, but the Mega 328 requires a low to reset it. So I'll just add a 7404 hex inverter right here. I'll give it power and ground. I'll be using the first inverter, so I'll just terminate all the unused inputs. Then, let's connect the output of the first inverter to the reset input of the Mega 328. Then I'll just connect the output from the Plague Mark II to the input of the inverter. Finally, I'll connect the tickler output from the Mega 328 to the Plague Mark II reset. It would be best to disconnect the reset switch from the Plague Mark II, but I'll keep it connected. We just need to make sure not to press the reset switch, otherwise we could short out the tickler output. Okay, there we are. Let's see if this works. Now the 10-second startup of the Mega 328 should be a little too long for the first watchdog timer loop, assuming that I've set the frequency of the Mark II clock correctly, about 2 to 3 Hz. So, what we should see is that the Mark II will reset the Mega 328. Then, during the second watchdog timer loop, the Mega 328 should enter its main execution code and tickle the watchdog. Let's power it up and start the clock to the Mark II. See that? We're now in the second watchdog timer loop after the microcontroller received an initial reset. And the watchdog was tickled. And we keep tickling it every 4 seconds. Now I'll put the Mega 328 into a lockup. And it recovered by restarting. Did you notice that the Mega 328 was only reset once? This is because the watchdog timer went into its second, longer loop after resetting the Mega 328. Let's try it again. There, it seems to work just fine. So, this was just a mock-up to simulate a realistic program we could write for the Plague Mark II homemade CPU. I would in no way use this in a real system, but it was just an example. In the next Mark II video, I'll work on completing the CPU design, and then we'll work on another mock-up test of the completed system. Well, I hope you've enjoyed the series so far, and I'll see you next time, right here on Dr. Plague.